Most electrical installations don't fail suddenly. They scream for help long before they break. By tracking power fluctuations with Industrial IoT, we can catch electrical faults before they cause a shutdown. Today, we are building the brain to listen to those warnings. Real-time motor power monitoring reveals hidden problems early, allowing IIoT systems to predict failures before downtime happens. By tracking voltage, current, power, energy, frequency, and power factor, we can detect early signs of bearing wear, misalignment, overloads, pump cavitation, or electrical faults long before a motor actually fails. This is also true for all other industrial electrical installations and home appliances. Let's create a real industrial scenario for this industrial IoT. Imagine a utility service system with several industrial pumps. In such setup, each pump motor could be monitored by a PZEM-004T energy monitor module. Since the ESP32 is the current top pick, these modules could connect to an ESP32 acting as a PLC to handle local logic and visualization. The ESP32 then connects to the Raspberry Pi Edge Gateway using Modbus ROTU, where Node-RED processes the data, builds dashboards, and prepares it for analytics and machine learning. But today, we will focus on setting up and hooking up a single energy monitor module to the Node-RED Edge Gateway. An earlier video at the top right of your screen shows a similar connection to the Remote XY cloud. Hooking up the PZEM-004T module to the ESP32 PLC is easy. Its TX pin is connected to the serial 2 RX pin D16 of the ESP32, the module's RX pin to the ESP32 TX pin D17, the 5V pin to VCC, and GND to GND. This option is suitable when the gateway is installed close to the pump. Otherwise, a TTL to RS485 converter module will be required at both ends to extend the distance. For the local power display, a 20x4 I2C LCD is connected to the ESP32 via the SDA pin on D21 and the SCL pin on D22. At the other end of the PZEM module, the external current transformer is connected to this input. The AC power supply neutral connects here, and the live wire connects here. The AC power supply live to the electrical load to be measured goes through the current transformer and then to the load. We will program the ESP32 with the FLProg version 8.2.1, which can be downloaded from the archive using the link in the description. Now, let's create a new FBD program for the ESP32. Drag the energy monitor block to the program and double-click to open the configuration window. Select Serial 2 to reserve Serial 0 for the Node-RED connection. Enable the reset inputs, the voltage, current, power, energy counter, frequency, and the power factor outputs. Let's now connect terminal blocks to the outputs of the block with their corresponding names. We can now start creating the logic for the local LCD by dragging the display block to another board. Double-click on it, add a display, and select the I2C connection type. Change the display row size to 4, the column to 20, and the I2C address to 27 for me. Set the constant as energy monitor, the row to 1, and enable centering. Invert the EN input of the display block. Duplicate the display block. Change the data type to inputs, the display row to 2, the column to 1, and connect a string concatenation block to the input. Increase the concatenation block input to 3. Assign small v column space to the first input and capital V to the third input. Connect the convert string block to the second input of the concatenation block and the input of the convert string block to the voltage terminal. Let's now copy these blocks into another board. Right-click to remove the constant from the convert string block input and connect it to the current terminal. Insert a small I column space to the first input of the concatenation block, a capital A to the third input, and change the display colon to 11. Repeat these previous steps to create a display for power with a small p and a capital V at the concatenation block input, the display row set to 3 and the colon to 1. For the energy, with a small e and kWh, row 3 and column 11 for the display. For the frequency, with small f and hz, row 4 and column 1 for the display. And finally, the PF positioned at row 4, column 11 of the display. We are going to connect the ESP32 PLC to the Raspberry Pi Edge gateway using the serial 0 Modbus ROTU. From the project tree, expand controller, communication, double-click on Add Modbus and select Slave ROTU. Expand the Modbus slave, Interface ROTU, UART. Double-click on UART and select serial 0. Change the speed to 115200 and ensure that pin PEDE is set to no. Expand variables, holding registers, and double-click on holding registers to add a Modbus tag for voltage with float data type. Ensure that the first and the second register numbers are sequential and not overlapping for the other tags. Add tags for current, power, energy, frequency, and power factor. Drag all the Modbus tags into a new board and connect them to their corresponding terminal labels. With this, we can compile the program and upload it to the ESP32. You should now see the voltage, current, power, energy, frequency, and power factor on the LCD. Now disconnect the ESP32 from your computer and connect it to the USB port of the Raspberry Pi Edge gateway. Log into Node-RED following the steps from the last video at the top right of your screen. For our first flow, we need to install the Modbus nodes from the Manage Palette menu option. Go to the Install tab, search for and install the Node-RED Contrib Modbus nodes. Now search for the Modbus Read and the Modbus Response nodes in the Nodes palette. Drag them into the canvas and connect them as shown. The debug node can also be connected to the Modbus Read node to display the monitored power parameters as debug messages. Double-click on the Modbus Read node. You may name it ESP32 Modbus Read. Since the ESP32 Modbus ID defaulted to 1, the unit ID should be set to 1. The Modbus function to read the PZEM parameters should be FC read holding registers with the starting address of 0. Since the 6 ESP32 Modbus float parameters are 2 bytes each, we should set quantities to 12. Then I will set the pull rate to 2 seconds. We need to add the ESP32 Modbus server from here. Name it ESP32 PLC and select the serial type for Modbus ROTU. Search for and select the right serial port from here. ROTU buffered serial type and the baud rate of 115200 to match that of the ESP32. Make sure that the unit ID is also 1. Then hit Update, Done, and deploy the flow. All things being equal, the Modbus read node should show active, and the power parameters should be updated below the Modbus response node. The debug messages from here should also update the parameters. In the next episode, we will move on to process live power data in Node-RED and build dashboards and alerts for preventive maintenance. You don't want to miss it, so hit the like button and subscribe to this channel if you haven't. If you want to see this setup on a different MCU, maybe an Arduino and its IDE, drop a comment below. If 10 of you ask for the same thing, I will build it. See you in the next episode.